Thank you so much for watching the AI Weekly Update series on Henry AI Labs up to the week of June 23rd, 2021. This will be a quicker video, just doing a quick overview of each of these things, and as always, the links to all the content is in the description of the video. We'll start off with the latest in deep learning with code data. Break it, fix it, unsupervised learning for program repair is a strategy to try to align the distribution mismatch between real bad code that we say you take this Python code that doesn't compile, and you're trying to train a fixer that can map this code into something that would compile and fix the error, and you constrain it with an edit distance and so on. It's trying to align the distance between these real human errors with Python code and then simulated changes like artificially adding a parentheses or random deletions and so on, any kind of say like data augmentation idea that you would add to the code to try to get training data and self-supervised learning to train this fixer algorithm. So it's an iterative algorithm that trains a breaker and a fixer that we'll get into more later. And so this is solving this problem kind of simulated to real, where we simulate these kind of environments with data augmentation in the program repair setting. And so we're also trying to bridge this gap between the simulated distribution shift to the real data. And SimGAN is another paper in the series from the Google AI blog. So we saw in a previous weekly update, RL CycleGAN and RetinaGAN. These are all trying to solve this problem of the simulated robot learning environments generalizing to the real world, in this case focusing on the physics parameters compared to previous works that looked at the visual parameters like lighting and so on and these kinds of ideas. So then in data augmentation, we have a new library from Facebook, Augly, that implements tons of augmentations for images, text. It's a pretty interesting library, and they have some collab notebooks that show you how to integrate this with, say, the torchvision.transforms and PyTorch and these kind of interfaces. So then we have a crop of new papers in natural language processing, starting off with scientific language models for biomedical knowledge base completion. This is looking at, say you have these relations where you have entity, relation, entity, you classify the type of the entity and so on, and they're used to fill out these knowledge bases from, say, a large corpus of like biomedical research papers. So this is the latest study on that and showing how well these different kinds of models can perform this, say, triplet ranking task and these kinds of ideas. And then we'll look at question answering infused pre-training of general purpose contextualized representations. This is this idea of trying to improve on the mass language modeling tasks. We've seen things like, say, SpanBERT, where you mask out more than one token, or Pegasus, where you take out an entire sentence and reconstruct the sentence. And all these kind of ideas, and like Electra, these kinds of ideas of building on the self-supervised language modeling task. In this case, we're using a question generation model to try to have more structure with when you take a mass span, try to have it answer all the questions that are reasonable given the context, and its way that the question generation system plays with the context as well. Then prompting contrastive explanations for common sense reasoning tasks. This has this insight that when you try to ask a model, why did you make this prediction, it's an incredibly open-ended question. There are many different ways it could answer that. So it's tried to constrain it with contrastive relations. So they give an example, say peanuts compared to raisins. Peanuts are salty, raisins are sweet, so on, this kind of comparison for explanations. Then in the field of natural language inference, document NLI is expanding the scope. So say it's not just a single sentence for the premise hypothesis pairs, but entire documents. And then unnatural language inference is showing that even if you randomly permute the premise and the hypothesis, you get the same prediction. So showing that the transformers, even though they are a set operation, they're supposed to be permutation of variance, which is fixed with this position encoding and so on, but they're still not. They still make the same predictions if you shuffle around the words in the premise and the hypothesis, shown in this paper. Then multi-head or single-head and empirical comparison for transformer training. Multi-head, they describe how it's this ensemble kind of strategy where you split up the query key value matrices, have like 8 different parameterizations of them, and then you aggregate them later on, compared to just having one head and so on. And the multi-head is kind of easier to train, and they show how to stabilize single head and train a 384 layer transformer where they show that single head is better than multi-head at that kind of scale. And then a survey, this is a pretty long 127 page survey on different applications of graph neural networks for natural language processing. So then in the domain of computer vision, we've seen a billion different papers that come up with different image transformer designs, and we've also seen an emergence of research that's trying to use these same pre-training tasks like language modeling for computer vision. So probably most notably is ImageGPT. ImageGPT uses the same left to right autoregressive modeling to predict masked out pixels. So BERT pre-training of image transformers is going to have this interesting alignment between a discrete vector quantized variational autoencoder visual token codebook and then masking out patches and then trying to use this kind of alignment as a strategy for making the BERT pre-training strategy with pixels work pretty well. And they show a really interesting ImageNet result by using this pre-training strategy similar to BERT for image. And then, so generative modeling for pre-training computer vision models hasn't performed as well as contrastive learning. So we have 2 new papers in contrastive learning as well, which continues to boom in interest. Long, short, temporal contrastive learning of video transformers. This is when you take video data, you encode it with this times former architecture, capital S in the middle of the word, where you compare, say, a 16-frame video sequence with a 14-frame sequence and try to align them as positive pairings if they belong to the same video clip, and that kind of sampling strategy. And then watching too much television is good. Self-supervised audio-visual representation learning, same idea, kind of, well, not the same ideas, but it's contrastive learning idea where you, say, are using the audio pairings of, it's a paper from Netflix. They have the audio that corresponds with the movies and TV shows. So they're using that to form the positive pair sampling, and then obviously audio from another movie, a TV show, some kind of strategy like that for the negative sampling. So then in the domain of understanding deep learning and kind of predicting the future and some interesting characteristics of it, deep learning through the lens of example difficulty has this perspective of you can kind of look through the sequential forward pass, and if, say, at layer 8, it's kind of already determined its prediction, then that's an easy example compared to a hard example, and there's a way of classifying hard, easy examples for the training of a deep neural network. Pre-trained models, past, present, future, telling the story of this pre-trained models, like the model hub and all this kind of stuff, and making some predictions about the future that I thought were pretty interesting. Counterfactual explanations in machine learning, challenges revisited. This is the idea of, say, an interpretability technique where you want to say, why did the model make this prediction? So you start to change the input values. So say if it denied a loan request and you say, well, if your income had increased by $5,000, that would be the counterfactual that flips the classification, and now you're granted the loan. This is a list of, I think, about 12 different problems with really using these counterfactual explanations for these machine learning models, notably that they're not actually structural causal models, and so on, and other kinds of things. And then reverse engineering of generative models is kind of an interesting idea where they take samples from the FFHQ or one of these face generation data sets, and they try to predict the hyperparameters of the generative model that had produced that image. So I'm not exactly sure why that's useful, but I think it's kind of an interesting thing to be flipping it like that and predicting the hyperparameters that produce the images rather than just generating the images and so on. And I'm not sure why that's useful, but definitely an interesting idea. And then thinking like transformers is an interesting idea, more computer sciencey with things like, say, formal languages and automata theory, like finite state machines, these kind of things. So putting the transformer, the sequence aggregation operations into a computation language, and then showing you how you do these kind of things like, say, the transformers as soft reasoners over language paper, showing how it kind of does this operation through this interface of sequence aggregation and sequence operations. So then in the domain of new code examples, as a reminder, Hugging Face is a course out explaining all sorts of different things in their library, from the auto model, pipeline, all these different things. They also have this integration with JAX now that's getting really interesting. They have an example with a Colab notebook that we'll look at that trains a language model in 18 hours, other details about the cost savings from switching to JAX for the Hugging Face transformers, all these really interesting things. And then an interesting demo of style transfer in the Hugging Face. Style transfer, say, transferring from casual writing style into formal writing style and these kinds of ideas, which I think is a really interesting way to disentangle content and style. This idea that you can transfer from style. We've seen things in images, obviously, the Graham matrices, neural style transfer, make like a picture of a dog in a Picasso painting style. And now they're doing it kind of in style transfer, not in the same kind of algorithm. It's more of like probably like a conditioning code and so on, not like a Graham matrix transformation. But anyways, it's an interesting demo of how to do it and implement the code if you want to, say, experiment with it for data augmentation or something like that. And then in the Keras code example series, amazing additions every week. We now have video classification with transformers, and also I'm going to cover it next week, but Ada Match has been implemented in Keras code examples as well, if you want to get ahead of that, but I haven't looked at that yet, and it'll be covered in the next week of AI Weekly Update. So then in the domain of, say, meta, just meaning I don't know how to classify each of these things, but we have a talk on geometric deep learning, amazing presentation style that I really like, and then unifying these ideas of translational invariance, set equivariance, this idea of graph neural networks, transformers compared to convolutional networks, and interesting ideas in geometric deep learning. I'm definitely not an expert on it, but this is a really fun talk to watch. Then we have a talk from Colin Raffel, learning from limited and imperfect data. This is a really interesting talk that unifies these ideas of entropy minimization, self-training, and then consistency training. And it's about a 30-minute talk. I think it's really interesting to watch, explaining kind of how fixed match works, this progress in, say, learning CFAR 10 with only 40 labels, and the history of, say, max out up to fixed match. And very interesting talk connecting entropy minimization, self-training, and consistency training, like what's used in say you have these data augmentation views and you try to make them consistent with the representations, and it's used for semi-supervised learning, so you have the unlabeled data point and so on. So then the Hugging Face Transformers 4.7 release, adding more computer vision models, which I think is an extremely interesting development with Hugging Face Transformers. And then this metadata set of the Model Hub, it's interesting because there's tons of models that people are uploading onto the Hugging Face Model Hub. And here's a metadata set that kind of describes it, which I think is really interesting. Then some new data sets, Feverus, Robust Bench, language annotated abstraction reasoning corpuses is the data set from Francois Chalet's on the measure of intelligence. This interesting, it's kind of like a few shot image generation problem is the way that I see it. You have these tiles and you got to learn the patterns and so on. Now they've added the language that tells you how to solve it and seeing if that kind of multimodal vision language helps with the abstraction and reasoning challenge. Another data set, learning to predict visual attributes in the wild. And then we'll look at another aggregation, Papers with Code newsletter, aggregating some more of the, the weekly news and just kind of grounding the AI Weekly Update series by looking at what, other kind of aggregation content is highlighting. So anyways, that's the overview of this AI Weekly Update. And again, this will be just a quicker video where I just quickly go through each of these things. And then the content links are all in the description of the video if you're interested in going deeper into any of these ideas. So first up is Break It, Fix It, unsupervised learning for program repair. And I've been really interested in this topic of deep learning for code data, especially ever since reading this paper, measuring code competence with the apps challenge. This is where they have these natural language prompts, sort of like a HackerRank leak code prompt, and then they have models like GPT-Neo solve the Python code, and it's pretty amazing the progress of that. So I think it's interesting to kind of keep an eye on what's happening in this space. So here's the latest advancement this week, Break It, Fix It, unsupervised learning for program repair again. So the idea is that you want to train a text generation model that can correct code that doesn't compile. You have this frustrating Python error and you want some kind of tool that can fix the Python code. So the problem here is they have three components. They have the critic, this is the compiler, this isn't a parametric thing, this is just whether the Python code compiles. Then you have the fixer that tries to fix the bad code and turn it into good code. And then you have the breaker. The breaker is like the data augmentation, the generative model that's going to try to break the code and try to simulate bad code so that you have training data for the model. So what they do is they also have a small collection of code that doesn't compile. And an interesting detail is about the class imbalance in these unlabeled data sets. So they describe this GitHub Python data set where they have something like 3 million Python programs. And then when they that they take from GitHub and then they put them through the compiler, and from the 3 million, only 38,000 actually are real examples of bad code. So it's interesting that out of 3 million, 38,000 are actual examples of bad code. But here's the problem that they're trying to address. So there's a distribution mismatch between real human errors and real bad code compared to the breaker and the way that it's going to try to break the code. So the breaker might try to just insert a parentheses or just delete, say, format, and to delete the T, so format, so it doesn't compile. And there's a distribution mismatch between how people actually make errors. So the solution they propose is this iterative algorithm where they have these iterations of only filtering the data that the fixer correctly fixes and then the breaker correctly breaks in this kind of way that makes it align with this original sample of bad code. So maybe later on I'll make a video that completely dissects this algorithm, but overall it's this iterative way of kind of refining the breaker's distribution to make it more realistic to the original samples of bad code. So Break It, Fix It is trying to solve this problem of the sim to real gap where the simulated environment thing is the breaker trying to break the good code and simulate bad code. So robotics and robot learning has been they are chiefly focused on solving this sim to real problem. So in a previous AI Weekly Update, we looked at RL CycleGAN and RetinaGAN. These are solutions to the visual domain mismatch, and this is presenting SimGAN, which is a solution to the physics parameters between the simulator and the real world. So what they've done is they replaced these differential physics equations with a neural network that's simulating the physics parameters. And so the way that they kind of structure this is by having an adversarial loss on the trajectories from the simulator and the real robot, trying to align these in order to provide some structure for learning these physics parameters. So it's not a direct loss on the physics parameters because it's hard to do that. So you just have this kind of like CycleGAN zebra to horses, like domain transfer simulated to real kind of way of mapping between the sim to real problem and using these CycleGANs, domain to domain, image to image translation, but more like video to video trajectories and so on. So then they also, once they do that, they also have a reinforcement learning fine tuning as well. So it has the adversarial stage, and then it has the reinforcement learning fine tuning. I'm not an expert on this research, but an interesting domain, sim to real, and all the different steps that are being made to try to solve this domain mismatch problem between, say, augmented data, generated data, simulated data, whatever it is, and then real distributions. So then also in this kind of domain, we have a new library for data augmentation from Facebook AI, Augly, a new data augmentation library to help build more robust AI models. And particularly this blog post describes how they're trying to do things like misinformation detection and how they want it to be robust to, say, screenshots and copies of content and these kinds of ideas. So they're turning to data augmentation where say you introduce this kind of screenshot style content copying as a data augmentation, and then you make your model able to detect these duplications because it's seen it in the training data, introduced as a form of data augmentation. So in this library, they have a few different augmentations. They have image, text data, video, audio, and then you can click it. You can come see a Colab notebook that shows example of how to use it, full list of available augmentations, and then quick demo of, say, how to stack this with the Torch Vision transforms and this kind of augmentation pipeline. So next up, we have an exciting advancement in the application of biomedical knowledge base completion with the use of language models and this fine-tuning task of knowledge graph completion. So the language models will be trained on, say, a big corpus of biomedical papers. We've seen a paper like SciBERT or BioBERT, where you train BERT on mass language modeling with these big data sets of, say, PubMed papers or medical archive, these kinds of data sets. So then they're fine-tuned with this task of predicting relations and ranking relations. So say the application domain of drug repurposing, where you're trying to find like drug target pairings or protein or like disease gene, these kind of relations. So you're trying to predict relations that aren't already contained in the knowledge graph and trying to use the language model to propose candidate, say this a head entity relation, tail entity. You're trying to use the language model to, say, generate the tail entity or the relationship between the two things. Say this is a protein, this is another protein, or I don't know, whatever it would be. And then you would use these kinds of models to rank these potential triplets to add to the knowledge graph. So I'm not an expert on this research, but here's the latest on the proposal that they're using, this kind of router. I think it's a way of selecting different models for different relations, as they have these different models that have been, say, only using language modeling or have actually had some supervised fine-tuning with the relation ranking task and these kinds of ideas. So if you're interested in this application domain, definitely something I'd like to check up on later. So next up in the space of improving language modeling pre-training, we have question answering infused pre-training of general purpose contextualized representations. So we've seen that language models perform pretty well at, say, the cloze test. The cloze test is where you evaluate the question answering ability by having it fill out mass tokens, and you kind of are just using the prompt as the question rather than having it in this, the usual question format of question and then, say, like mask to produce the answer to the question. A cloze test is where you put like the answer in the middle of the question as context. So it's not quite this question interface. And they're trying to move the language model so that they can more naturally handle this interface, similar to how like GPT, any GPT model has this left to right autoregressive. So the prompt is in the left side and then the mask, so question, mask. And there are papers like meta-tuning the prompts where you kind of fine-tune the models so that language modeling is more akin to seeing this kind of style of question, mask, because it doesn't see this that often in these data sets where usually you're predicting the mask in the middle of the sequence, and that's why the cloze test is maybe like the first proof of concept of saying that, how much knowledge can you pack in the parameters of language models? Can language models be like this schema-free databases where you can just query them and have them retrieve any kind of information from text and so on? So here's the latest paper on trying to improve the pre-training strategy. So they have a question generation model. The question generation model uses the context to generate reasonable questions, and then you use that as additional training data for this mass token being the answer to the question. So the idea, as they say, is that it should be able to answer any question that is reasonable for the context, and you use this question generation model to produce this context. So an interesting update to the pre-training of these language models. Explanations are an interesting direction for improving language models. When it produces a prediction, maybe ask it, why did you produce this prediction, then having the mask and seeing if you can just use that same mask interface to produce an explanation. That's kind of what's explored in the paper Why T5, where you use the T5 unification of all text tasks and to try to add explanation, explain why you made this prediction, or say give it a text classification example with the label in the prompt and then why is that the label, and generate it, and so on. So this paper is describing how that's a pretty open-ended idea to just have it, generate any kind of explanation. So more particularly, they think the better idea is to construct these contrastive prompts. So, rather than just having it say, why did you make that prediction, you compare peanuts with raisins. And so these would be the masked parts of the explanations, and you fill out the entities from the question or whatever the context was to kind of guide these explanations. And so next up we have a new data set, DocNLI, a large data set for document level natural language inference. This is trying to build on natural language inferences where you have the premise and the hypothesis, and you see if the hypothesis makes sense with the premise. Like, I don't like pizza, I had pizza for lunch, contradiction because you just said you don't like pizza, and so on, that kind of idea. So this is trying to build it into bigger data sets so that you have more context that you need to model, and making it a more interesting problem of natural language inference. There are a lot of interesting papers that are unifying natural language inference and question answering and all these kinds of natural language processing tasks, but natural language inference is a particularly interesting problem where you have this kind of pairwise classification, pairwise kind of reasoning task, and here's an extension to the data sets that are used for it. This next paper, Unnatural Language Inference, is showing that these models aren't that robust to the ordering of words in the premise hypothesis pair. So as shown in this table, what they're doing is they're scrambling around the words you see, boats in daily use, lie within feet of the fashionable bars and restaurants, and then you just scramble it, so restaurants and use, feet of fashionable, so on. So you're scrambling the words, but the model's still making the same prediction. And to me, it kind of makes sense because the transformer is supposed to be this permutation invariant graph neural network that is robust to switching it around, but then you use like the sine, cosine embeddings or learn position embeddings to try to make it do this left to right reading and so on. But they're showing that it's not robust to scrambling around these words. Maybe you could use data augmentation to try to make it more structured on this, have explicit consistency training where this should be a different representation than this, and so on. But here's showing this kind of behavior. Next up is multi-head or single head, an empirical comparison for transformer training. So multi-head attention is where you say break up the query key and value matrices, so you have like 8 or 16 different parameterizations of them, and it's kind of like, as they describe in the paper, like an ensemble learning technique where you have this ensemble of the different features that come out of each of the different attention heads that you aggregate into the features. And as they describe, this helps with training stability. So it's easier to train these multi-head models than a single head attention heads as you stack up, say, 384 layers or a lot of these layers. So they compare how, say, the 24 layer 16 head BERT large has the same attention and has the same model size as a 384 layer single head, but this one has more training stability with the multiple heads. So they show how to stabilize the training, and then as they show that this training difficulty isn't a bottleneck anymore, the deeper single head transformer achieves consistent performance without having to tune the hyperparameters too much. So an interesting study into this idea of multi-head or single head attention, taking apart these architectural details of the transformer neural network. So if you're curious about graph neural networks, here's a survey through graph neural networks for natural language processing showing different applications: graph construction, graph representation learning, and these other ideas like graph to sequence, graph to tree, graph to graph. So things like, say, having a knowledge graph where they use to do multi-hop question answering, or say you have like a syntax tree that you're parsing with these graph neural networks on a sequence input. So all these different ideas, if you're curious about this branch of research of graph neural networks and then trying to find natural language processing applications and the state of the art on graph modeling and the state of the art on each of the problems described. So next up we have BEIT, BERT pre-training of image transformers. And as you see from the bottom, we have a very exciting result. Large size BEIT obtains 86.3% ImageNet top 1 accuracy only using the ImageNet 1K dataset. So it's not using, say, the JFT 3 billion as in the latest Scaling Vision Transformers paper. It's just using the 1,000 labels ImageNet dataset to learn this representation rather than using some massive unlabeled data set for some kind of semi-supervised or self-supervised learning transfer pipeline and so on. So here's the idea behind the paper. So they use this, they have two parts of it. The first part is having this discrete codebook and then having the image patches as they describe. They tokenize the image into discrete visual tokens. This is used through this vector quantized variational autoencoder. And as a reminder, here is a great blog post for understanding what's going on with the vector quantized variational autoencoder. I'm going to link this in the description of the video as well. And a video from, I think it was maybe 3 weeks ago in the AI Weekly Update series, we looked at this, but here's the blog post if you want to understand that part of the, that learns this visual token codebook. So basically what happens is you take the original image, you map it into the discrete token. So say this is in this case, just let's use the same 4x4 grid. So say you compress this into a 4x4 grid of discrete tokens, and then you map this into 4x4 pixel patches. So it's 4x4 where each of the pixel sizes could be 16 by 16, but overall you have the 4x4. So you mask out, say, this block, and then you try to predict the discrete token. So you mask out this patch, and you map it into this position of the discrete token. So you match these two representations in the pre-training objective. and then you would fine tune this model for classification tasks. So the other successful self-supervised representation learning task has been contrastive learning in computer vision, in addition to, say, the generative modeling, that the BEIT style denoising autoencoder generative task, or say ImageGPT and so on. The other strategies that has been successful is contrastive learning with things like MoCo, BYOL, SimClear, SimSciM. So here's an approach on using it for video data with contrastive learning between long, short, temporal video frames. So they use this Timesformer architecture, as I show here. It's kind of similar to that paper on like self-attention between data points, where they stack the entire frame and then they have attention within each tabular column and then across the entire stack of the tabular data. If you've seen that paper, it's covered maybe 2 weekly updates ago, but it's similar of having this alternative attention between the time scale and then the spatial scale for how they're designing the transformer design with video data. So basically you're contrasting with, say, T minus delta, where you could have an even split where this is, the last 4 seconds, these are the next 4 seconds of the video, or more like the frames, because 4 seconds is like 120 images in video data, 30 frames per second, that kind of idea. So they're contrasting between long video sequences and then short video sequences, at least as far as I've read this paper. In this other paper, watching too much television is good. Self-supervised audio-visual representation learning from movies and TV shows from Netflix research, pretty interesting. So another idea where they are trying to use the contrastive pairings based on the audio pairings of the video data, and that's how they're forming the positive pairs compared to, say, audio that comes from another TV show clip or something like that. So next up, we have the latest research on understanding example difficulty in the title, Deep Learning Through the Lens of Example Difficulty. So the insight of this paper is that they have these K nearest neighbors classifiers that are built from the embeddings of each of these intermediate layers. So say you take the representation at layer 3, and then you use that to build the index of the data set, and then you have K nearest neighbor classification. So they find that the examples that you can do this pretty well in the earlier layers are the easier examples compared to the harder examples that you do later in the layers, and so on. And I haven't completely read this paper, but it's another interesting idea, and understanding this idea of example difficulty, which is useful for, say, curriculum learning, and overall just understanding what's happening with the training data and how the deep neural network is being updated. Pre-trained models, past, present, and future, is telling the story of, say, transfer learning, the Hugging Face Model Hub, and how we have these, pre-trained on language modeling, and then we transfer them into self-supervised learning tasks, or we have these, domain transfer, where you could train it with supervised learning on one data set and then transfer it to another supervised learning data set, like the ImageNet setting, and so on, with the end making some predictions about the future of these, of pre-trained models, and what will be, how this kind of paradigm of taking these models that are pre-trained and using them for some other tasks. So they discuss new architectures, like the development and, say, long form or lin form, like these transformers that can attend over more than 512 tokens, new pre-training tasks like, say, Electra, or what we looked at with this question-infused pre-training, the QUIP paper from the beginning of the video, and then beyond fine-tuning. So say they have an interesting strategy with these GPT models that are called prompt tuning. So prompt tuning, they have discrete prompt search, where you're looking for natural language prompts, compared to continuous embedding prompt tuning, where you say, you have the continuous embedding table, and then you're optimizing the continuous embeddings to adapt it for some tasks. There are things like adapter layers, all these other ideas of trying to fine-tune models without actually fine-tuning, say, a billion parameter model. You just want to try to, guide it to the task with as minimal parameters as possible, evaluating the reliability, multimodal, multilingual models, problems with computational efficiency, like, how do you fine-tune these big models, and how do you really pre-train them, and so on, like data parallelism, all those ideas. Then ideas like uncertainty, OOD, generalization, robustness with these pre-trained models, and then all these other kinds of ideas of maybe kind of bridging into probing the knowledge in these pre-trained models, and say things like closed tests, or these other ideas like language models as databases, and so on. One of the leading solutions to interpretability, or understanding why a model made the prediction it did, is trying to ask what-if questions or having counterfactual explanations. So, if the input data point were x prime instead of x, then the output would have been y prime instead of y. So as they describe with this example, if you're applying for a loan application, you might try to produce the counterfactual. So say if you had increased your savings by $5,000, then it would have been approved. So that's perturbing the x to x prime to flip the y to y prime. So this article is describing why this doesn't really work so well in practice, with one being the lack of structural causal models. So say you can, when you're changing x to x prime, you could adjust the age and the degrees. So say, you're 32 with 3 degrees, and then you change the age, so now you're 28 with 3 degrees, or whatever. These kinds of ideas where you can just like change it, even though you're breaking these causal pathways and these, relations, and I'm not an expert on that, but here's an interesting article kind of describing these problems with these counterfactual explanations and why this isn't such a great solution to interpretability with these predictions. So here's a pretty funny idea. The paper is titled Reverse Engineering of Generative Models, Inferring Model Hyperparameters from Generated Images. So they all have the same data set, and then they have different hyperparameters that produce these images, and they're predicting the network architecture or maybe the loss function, these kinds of ideas. So you're predicting the parameters of the generative model that had produced this image, and I think it's an interesting kind of idea. These are examples of the hyperparameters they're predicting, like the neural architecture search, design, space configuration of the model, and so on. And I'm not sure why this is useful, but one idea is, say, deep fake attribution, where you try to say that this would be produced by this kind of model if it is a deep fake, and so on. That's one kind of solution to deep fake identification. So next up, another interesting paper that came out this week is titled Thinking Like Transformers. And so they construct this computational language about these sequence aggregations. And I'm not really an expert on this work. I'm not sure exactly why this is useful, but it seems like an interesting way of thinking about how it might be able to do these different tasks. And they describe how it can do, I think it's something like addition or summing up the sequence lists and so on. And they describe how they combine these sequence operations. So I don't know too much about this, but here's an interesting paper just to kind of complete the summarization of the new stuff this week. So to just kind of come back to this, Hugging Face has put this course out on how to use these models. You see the chapters, transformer models, what are they, encoder, decoder, sequence to sequence, so on. Using Hugging Face transformers, models, tokenizers, handling multiple sequences, putting it all together, fine-tuning a pre-trained model, using the trainer API, and then sharing models in Tokenizer, the model hub, using pre-trained models, and all that. So really great course on using this cutting-edge library of Hugging Face to do research in emerging not only natural language processing, but they're starting to develop more computer vision, and it'll probably be the host of all these pre-trained models, and I think probably the future of Hugging Face is bright. So as one example of what you can do with Hugging Face, if you're curious about training your own language model from scratch, maybe you have some custom data set and you want to see how well it can do these question answering closed tasks, this kind of idea, or you want to do the transfer learning, fine-tune the representation for a supervised learning task, here's how you can implement this using the JAX backend. So this is an example of how to do it. This is their example of how to train a custom one with this Oscar data set, and they show you how to train your own bypair encoding tokenizer and all that. So here are probably the interesting thing to see for this particular article. You see the Flax backend, the JAX Flax. I'm not sure what the difference is. I think Flax is maybe like the compiler thing similar to XLA and PyTorch, something like that. But anyway, so the cost is $124 to run this for 15 hours on the, I think this means the 8-core TPU machine. I'm not exactly sure about that. Compared with 8 GPUs with PyTorch that has, let's just say 8x the cost and then 3x the time to do it. With this 8 GPU PyTorch thing compared to this TPU XLA compilation, I think is what that means, and so on. So anyway, so you see the gains in cost savings and time. So here's another example of what makes Hugging Face so interesting. They have this model hub where people upload pre-trained models, and then they have a hosted inference API. So linked in the description of the video will be this informal to formal style transfer model. So you can put in text like, you have to go to Canada because it's cool, and it'll translate it into formal writing style, you have to go to Canada because it is cool. So this kind of style transfer is a very interesting kind of idea. I think for maybe data augmentation, you could use this kind of transformation, and these kinds of ideas, informal to formal, or say like scientific writing to blog post style writing, all these different kinds of ideas of text style transfer, which is an interesting idea in natural language processing. So next up in the Keras code example series, we have video classification with transformers. Building on the previous video classification with the CNN-RNN architecture, using the UCF 101 dataset to classify actions like videos of people playing tennis or cooking or whatever. And so now this is how you use the positional embedding and the transformer encoder to process this video data and classify video data with the transformer model. Also new in deep learning this week, here are a couple of talks that I highly recommend watching. A talk on geometric deep learning that is really well produced. And then Learning from Limited Labeled Data Conference is a playlist of all these different talks. And this is about about entropy minimization and unifying the ideas in, say, entropy minimization, where you're just trying to have confident predictions and minimize uncertainty about predictions, and then comparing that with the self-training approach and how that's entropy minimization, and then relating how consistency training is similar to entropy minimization. And this Half Moon's plot describing this idea of having these kind of classification boundaries and how entropy minimization helps form these decision boundaries. Overall, really interesting talk, and I highly recommend watching both these talks. So here's another interesting announcement from Hugging Face. Transformers 4.7 has been released with the DETR model from Facebook AI. DETR is this like transformer object detection model. It has like this bijection training loss thing that it's used to, do the bounding box prediction. So overall, showing that this Transformers library is moving more and more into supporting computer vision models. So here's another interesting idea, the Hugging Face Model Hub dataset. This is a tabular dataset that contains information about all of the pre-trained models that have been uploaded to the Hugging Face Model Hub. So it has the model card README and describes how it has each of these models, the ID of the model card README, say tags, list of files, library downloads last month. So interesting metadata about all the different models that are uploaded to this Hugging Face Model Hub. And again, you can go to this inference API if you want to test things like, say, they have text generation interfaces, or they might even have like few shot classification, or you could just quickly load it into the Hugging Face pipeline interface with, say, fill mask or the classification where you give it the labels and so on. These ideas that you could learn more about in the course that they provided. So here's a collection of new data sets and benchmarks that came out this as well. First, fact extraction and verification over unstructured and structured information. So similar to the Fever data set of claim evidence pairs labeled as refuted, supported, or not enough evidence. This is particularly about like tables of information in Wikipedia and reasoning over data that's organized in this table format. I think unstructured means that it's a blend of the tables as well as just the usual Fever style claim evidence pairs. So then we have an addition to Robust Bench. This is a benchmark for adversarial robustness. So these different models are evaluated on, say, like these, these adversarial attacks where they perturb the pixels and try to cause misclassification. So then the LARC dataset, language annotated abstraction and reasoning. This is where there are language instructions for the ARC tasks, which are like these kind of like puzzles that you have to generalize to how the pixels are kind of moving in these patterns in the pixels that are hard for machines to do, easy for humans to do, and so on. Then visual attributes in the wild. This is the latest data set in, say, object detection and annotating these objects at a large scale, and interestingly also having explicit negative labels for each of the bounding box annotations. So next up, we're looking through the Papers with Code newsletter. These are things that have been covered in past AI Weekly Update videos as well. The self-attention between data points paper was really exciting. This is you say you have a tabular data set and you flatten it out so you have the d-dimensional tabular records and then all n of the entries that you have, you stack it all together, and then you have this attention across the data set and then within each of the individual records. Scaling vision transformers using this JFT 3 billion data set, or this might be the compute metric as it goes across. But anyway, so these are the scaling laws of these vision transformers. So they have more pre-training data. This decision transformer thing where they're using offline reinforced learning to generate sequences of action trajectories and showing that this performs better than, say, like Q-learning or whatever with this offline reinforced learning setting where you can't sample data. Out of distribution detection with pre-trained transformers, showing that these these big transformers are performing better, like the CLIP model, at this task of out of distribution detection, like, say, train on MNIST and then detect near OOD like Street View house numbers, or far out of distribution like trained on MNIST and then CFAR 10 images, something like that. And then some other papers that are interesting linked in the Papers of the Code newsletter, some training data sets, different coding libraries, and then some different Papers with Code particular announcements. Thank you so much for watching the latest AI Weekly Update from Henry AI Labs on the week of June 23rd, 2021. Hopefully you found some content that's relevant to your research. Please subscribe for more deep learning and AI videos.